Welcome to the last video for the exam of 3 April 2020. Let's continue with exercise 7. So we have a universe consisting of the elements 1 until including 5, and we have a corresponding array with the values corresponding to the indices. They ask us to fill this sequence in such a way that the property is true, so that this universal quantifier will give me a truth value. So let's try to read it. So for all elements, and when we're talking about an element coming from the universe, we give it a name and we call it I. For all those elements, xi must be some sum. Okay, let's try to work out this sum. So just for an example, let's take I being 1. Then xi, so x1 in this case, should be the sum of all elements coming from that same universe where j is smaller or equal 1. And what do we summarize? We summarize the indices itself. Okay, for 1 that's doable. And so j must be smaller or equal than 1. That's only 1. Okay, so this should be 1. I is 2, then x2 should be the sum of j element u and j smaller or equal 2. And what do we summarize? The indices itself. So now we have to count 2 elements, namely the element 1 and the element 2. That gives us 3. I is 3, and do you already recognize the repetition? So x3 will be 1 plus 2 plus 3, will be 6. I is 4, then x4 will be 6 plus 4 being 10, and the last one, I is 5, will give us x5 will be 10 plus 5 equals 15. So the sequence they're looking for is the sequence 1, 3, 6, 10, 15. Let's look at question B. So again, we have a sequence of 5 elements, and now we already have a filling. So the values are -3, 5, 0, 3, and 12. Give the value of the next expression. So for all elements, and we call them I comes from the universe, so that was 1 until and including 5. There is a j from that same universe that xi is smaller than j, xj. Okay, it's a universal one, so we have to check them one by one, and if we found a counterexample, we're done, and otherwise we'll just have to continue looking for it. So let's start at the beginning. I being 1. Can we then find a j in such a way that xi and x1 is -3? So in such a way that -3 is smaller than xj. No problem, because -3 is smaller than 5, is smaller than 0, is smaller than 3, is smaller than 12. So that is no problem. This one will work. But if we look at the universal quantifier, then apparently we should look for the largest possible number to find a counterexample. And the largest one is 12. So when I is 5, then x5 is 12. Okay, so can we now find a j in such a way that xi, so this 12, is smaller than xj? And of course we can't, because 12 is the largest number present in the sequence. There is no larger one. So I've got a counterexample. So the complete universal quantifier will give us a false, because I found one counterexample for I is 5. Then the second part, max value. So we are looking at an index I coming from the universe with the restriction that I is even. So that means I only have to look at I being either 2 or 4. Now those are the only even numbers from the domain U. And what do I evaluate? The corresponding values in the sequence. So I have to look at x2 and at x4. Well, x2 is 5 and x4 is 3. Okay, and the max of these two values is 5. So the answer is 5, the maximum of value x2 and x4. That's it. Okay, this concludes the exam. I hope you managed to do it with or without my help. If you have any questions before the exam, please contact me on the Teams meeting or just send me a mail. And because we have plenty of time on this video left, we're going to add on this video the difficult induction question we skipped from lesson 4. So exercise 4.11. Please note it's really just for fun. So if you had enough of math, then just end the video now, and otherwise just join me in this exercise. And the difficulty here in this exercise is that we're working with 2 base values and with a successor which is depending on 2 predecessors. Now, if we'd like to read this one, so R0 is 1, R1 is 3, but R2 is based on 2 times the previous one, so 2 times R1 minus the first one, R0. So it's 2 times R1 is 6, minus 1 is 5. So R3 would be 2 times R2 minus R1. So that would be 2 times 5 is 10, minus 3, that would be 7. And so every element is depending on 2 elements before it. So we have to have 2 base values to start with. So that makes this exercise a little bit complicated. But let's try if we can manage. So still we have to work with step 1. So step 1, prove that this statement here is true for the first element. And in this situation you should read for the first 2 elements, because we have 2 base values. So to prove that R0 equals 2 times 0 plus 1, and prove that R1 equals 2 times 1 plus 1. Okay, R0 equals 2 times 0 plus 1, that gives us 1. And if we go a little bit up, that was the definition. Check. And R1 is 2 times 1 plus 1 equals 3. Again, according to definition. So we need to check 2 elements, but still it's administration. No big deal. Step 2. And also for step 2, we have to make 2 assumptions, because Rn plus 2 is depending on the 2 predecessors. So assume that it's true for Rk and for Rk plus 1. So now we have 2 elements for which we have to assume it's true, and then we need to prove that now indeed Rk plus 2 will fall as well. And so R0 and R1 is true, okay, R2 will fall. 1 and 2 is true, okay, 3 is fall. Exactly. So the idea of the basic truth finding is exactly the same, but only with 2 base values and 2 assumptions. So let's make the assumption. So assume true, Rk would be 2 times k plus 1, and Rk plus 1 would be 2 times k plus 1 plus 1. Those are the assumptions we make. So these are the things we can use in our proof. And then we need to prove that it's true for Rk plus 2. So to prove that rk plus 2 equals 2 times k plus 2 plus 1. Okay, let's give it a go. Proof. So we have to start on the left. So rk plus 2. What do we know? We know by definition that rk plus 2 is r, and I have to go up to check, is r 2 times rk plus 1 minus rk. So it's 2 times rk plus 1 minus rk. Okay, let's use the assumptions. So this would be 2 times rk plus 1. So it's 2 times k plus 1 plus 1 minus rk. So that would be minus 2k plus 1. Okay, let's simplify this. So this would give us 2 times 2. So that would be 4k plus 2 times 2 plus 4 plus 2. Okay, minus 2k minus 1. So that would give us 4k minus 2k would just give us 2k plus 4 plus 2 minus 1 plus 5. Okay, is that the same? Now let's see. 2 times k plus 2 gives us 2k plus 4 plus 1 give us 2k plus 5. And indeed, and now we have an exact match. Perfect. So with the help of mathematical induction, and with the help of 2 base values and 2 assumptions, we have proven that now by just starting with 2 truths, everything will tumble as a complete domino. So we have proven the statement. Okay, a little bit tricky. It will not be asked on the exam. So on the exam we will only work with 1 base value and 1 relation with a successor. So again, for those of you who managed to do this one as well, well done, and let's hope you get a perfect result on your exam.